Welcome to AASHTO Resource Q&A. We're taking time to discuss construction materials testing and inspection with people in the know, from exploring testing problems and solutions to laboratory best practices and quality management. We're covering topics important to you. Now, here's our host, Brian Johnson.
Welcome to AASHTO Resource Q&A. I'm Brian Johnson.
And I'm Kim Swanson. And who do we have with us today, Brian?
Well, today we have a special guest, Dr. Azizinamini, Director of the Infrastructure and Sustainability Department at Florida International University in Miami, Florida. Atarad, welcome to the podcast.
Thanks for the opportunity to be with you.
And now, before we get started with questions, I just want to introduce our audience to the concept we're going to talk about today. The term is becoming more and more popular in civil engineering, and that term is resiliency. To me, this term represents recognition that engineers need to now design not just for conventional purposes or applications anymore. Engineers need to design for potentially catastrophic events such as, a 100-year flood, hurricanes, rising sea levels, extreme temperatures. And it really doesn't seek to determine why these things are happening, but instead just the understanding that these things are happening and that engineers need to design around them to protect or make the infrastructure more resilient, hence the term resiliency. But that's just my layman's explanation of what this is for our audience. But we have our special guest here who is an expert who can probably give us a better definition. So, Atarad, how would you define resiliency?
I think there has been many different definitions of the resiliency, but really resiliency means that you need to design the buildings and the constructed facilities so that they can return to the full function that they were designed originally. Soon after the extreme events, like a hurricane, for example, let's say, or the flooding that you can have. In our case, let's say in a coastal area, where we are dealing with the salt water and the corrosion issue. Really, the resiliency means that to be, in my mind, is to be proactive and do whatever that we can do so to prevent the damage. Because if you have a damage, it's going to take a time before you can repair it and then return the building or the constructed facility back to the full functionality. So in my mind, in the coastal area, especially where we have the hurricane and so on, really to be proactive and do whatever that we can do to beef up or upgrade the existing constructed facility so that they don't sustain the damage. That's the best way to really to return it back to full functionality immediately. It means that there is no damage. Well, because once you have a damage, it's going to take time to repair it. And it's going to paralyze the economy, the functionality, and the people's daily life.
Absolutely. Now, you've been at this for quite some time, right? Working in this field. What first got you interested in this?
I think more than anything else, probably because of the location, Miami. I mean, Miami is a ground zero when it comes to the issues related to the resilience. I've been here since January 2011. Fortunately, we haven't had a major hurricane that has hit, for example, the area. But there's a lot of preparation that goes. People get really concerned about, for example, when there's a prediction that is of a, let's say, major hurricane that's coming. So continuously we think about that. So from sometime in the June to the November, now to December, seems like the period that we have to be concerned about the hurricane is really increasing. So I think it's more has to do with the probably where I'm at, and I really have paid more attention to the concept of the resiliency and designing the constructed facility for resiliency since I've been in Miami area.
Now, when it comes to this topic, the items that make the headlines are the building collapse, the bridge getting washed out, or the road getting washed out. But you touched on an issue that I think the traveling public doesn't think about a whole lot, which is corrosion. What is the impact that, you did mention the water covering these structures is going to lead to corrosion, but what really happens that's so damaging about corrosion, and how long can it take for the negative outcome to occur when corrosion begins?
Yeah, the corrosion issue, first of all, we as a structural engineer, we are very good. That's a bit of background to tell you. We are extremely good if we say, for example, give me a beam and I'm going to have so much load, and we have a mechanics, basically our design equations, so we can design it to resist the, let's say, the load. We can calculate the stresses and then put enough material in it that provide the resistance that is needed. But as a structural engineers, really, we don't quantitatively try to assess and design for the corrosion. I mean, corrosion, you can have basically especially with the steel element that are embedded in a concrete. So the concrete provides a protection for the steel reinforcement. But you have a salt water, and the chloride kind of seeps through because the concrete is a porous material. So the chloride itself really doesn't cause a corrosion, but it ingresses through the concrete and then destroys the film, the protection film that the concrete is providing for the steel reinforcement, and it causes basically crack initiation, and then the corrosion starts. Once the corrosion starts, then you are dealing with the material that's is going to be taking more space, and it causes the expansion of the basically inside the concrete and the cracking. And unfortunately, it's very difficult to see it until you see the cracks outside, and that's probably it's a little bit too late. Now, in the coastal area, we have two ways. There's the carbon-induced, basically corrosion, and there's also the chloride-induced, basically corrosion. And there are some tools that you can predict how long it takes, right? But those tools that we have to predict, for example, it's called technical term, the error solution to the fixed second law, for example, that we can use to predict how long does it take for the chloride to reach the steel level. But there are many assumptions that goes on in there. But the factor of safety could be 4. That's ridiculous. I mean, that means basically you are just crossing your finger that, hey, nothing bad is going to happen. Let's say in the case of bridge elements, for example, we do a fantastic jobs to design something for the strength, but then after we design for the strength, and then we come back and then do some selected certain details, and then we say, okay, now we have designed it for the basically against the corrosion. But I think in my mind, I think we have to be in a very quantitative manner. We need to design for corrosion the same way as we do for the strength. One more point, in my opinion, if you design, especially in the case of the bridge, buildings are a little bit different. In the case of the bridge, if you design, let's say, a bridge deck against the corrosion, again, which is service life, I call that service life. If you design first for service life and then check for strength, you're going to find out the strength is a bonus. You're going to have so much strength that you won't need. So what does that mean? I mean, that really points out something that I've been kind of preaching in recent years, and that is we need to make a fundamental change in our approaches in design, especially with respect to the bridge. Not every element of the bridge, but there are a good number of the bridge elements that we need first design for service life and then check for the strength. That means, in my opinion, it's a time to take a step toward development of the next generation of the AASHTO LRFD code. Now, this is a very probably loaded statement that I'm making, okay? But if you think about that, and it really relates to the resiliency too, there are very few examples that you can find that the bridge element, the bridge have collapsed because extremely heavy, this humongous load have passed over it. It does happen in the rural area, the steel truss bridge and all that. But it's not the common. But what is common is the collapse of the bridge because of the corrosion. And where do we spend most of our time? We spend most of our time in design for strength. And we cross our fingers so that it has a service life. And that's why in recent years, I've been preaching that really it's time for us, I think, to Just like the fact that in the 80s, we switched from the AASHTO bridge specifications, which was an older version, to development of the AASHTO LRFT bridge design specification. That was a major transition. I think now it's time for us to take a step to develop the next generation of the AASHTO bridge design specification, one that for most bridge elements tries to address the service life. It doesn't matter in which order, but in a very quantitative manner, not just by selecting the details. And you're going to find, for example, a bridge deck. If I design a bridge deck for service life, trust me, you're going to have so much thickness in there that the strength is going to be just a number. Hardy Cross, actually, in 1940s, he made a statement, and I don't remember exactly which one of his books was that. He says, strength is a number. Other than that, doesn't mean anything. So,
and yet we have hung our hats on strength, right? All these years. So what you're saying is we should have a fundamental change in the way we're thinking about what makes a bridge good. What's the point, right? Like we kind of assume these bridges are going to stand forever, but obviously that is not the case. So how does one design for that service life and for ensuring that you don't have these issues with corrosion and other problems that you've seen pop up?
Well, there are many things that, for example, in the recent years, I think some advanced materials have also become available. For example, ultra-performance concrete. Ultra-performance concrete, in my opinion, I think it's a future of not only the bridge engineering, but it's a future of the structural engineering, in my opinion. I think ultra-performance concrete has opened a new horizon. And now it is allowing us to do things that we were not able to do. For example, I work in an accelerated bridge construction area, ABC, right? And one of the there are three different methods of the trying to design or construct a bridge using the ABC method. And the most popular one, okay, it's a SPMT, it's a lateral slide, and then it's a modular approach. The modular approach is the most used technique. ABC technique is a modular. What the modular means is that you take it, let's say, a steel beam or a concrete beam, you take it, put a concrete deck on top of it, and that becomes a one module. You get about 4 modules, you bring it to the site, and you reduce the number of the construction days, and then you attach them together, which is a joint. Now, the common sense in the bridge engineering says the less joint you have, the better off you are. Now, here we have a ABC, which is a great idea because you're reducing the number of the construction activity days on the site. The total construction time doesn't decrease. It's just an on-site construction, right? But then you have these joints. Now, if you use the ultra-performance concrete to connect them together, you will have a solid structures. So it is allowing us to do closure joints, for example. The other thing is that ultra-performance concrete, one of the reasons that, in fact, bridge industry is way ahead of the building industry in use of the ultra-performance concrete. I think it's going to get more popular. One of the reasons that last few years, I would say, look at maybe 6 years ago, 7 years ago, people were hesitant to use because of the price. But now there are many universities, including our University Transportation Center, ABC UTC. We have developed a non-proprietary UTC. PCI has developed. Good friend of mine, Meher Tadros at the University of Nebraska, Lincoln, and with his team, they have developed this non-proprietary UHPC. University of Michigan has developed it. New Mexico has developed it. Several other. So this non-proprietary UHPC is now becoming available, and the price, everybody agrees, somewhere between $500 to $800 per cubic yard, whereas the commercial version that's out there are in the order of $4, $5. In place, it can cost you, I've seen number $10,000, $12,000. The reason for that high price is because when you get the commercial version, you have to get their technicians, you have to get their mixers, you have to get this, and that adds up. It's not just the material. But it's not a brain surgery to make a concrete mix. Our graduate student makes a UHPC in the lab, so everybody can do that. The contractors are much smarter than in the field than our graduate students. So to make it long story short, I think the UHPC, I think it's a future. And one of the things that was blocking the use of it was the price is going down because of the availability of all these non-proprietary UHPC now. So you wrap it. If I may just add one to why UHPC can really help. Let's say, for example, if I take we have one concept actually that's called the UHPC shell. So what we do, we replace the formwork with the UHPC. Now we are printing it. We are printing basically the formwork with the UHPC, right? Imagine you want to make it just a box, rectangular box, very simple, right? We have printed 12 feet wide, 12 feet long, 14 by 14 inch box using a UHPC, using a 3D printer, using a printer that we have developed ourselves, right? So now imagine you want to, that box is a, let's say, cap beam. I'm just giving an example. So you can print it, right? It's just an 1.5 inch thickness the walls. You can take it to the field. You can put the steel cage in there, and then you can fill it with even lightweight concrete, right? Now you have eliminated the time that it takes to build the formwork on the site. You're eliminating the time to go back and remove the formworks. You have made your structure resilient because what's inside is probably going to be protected for life. Nothing penetrates through the UHPC. The rapid chloride permeability numbers that we are looking with UHPC is an order of 50, 60 coulomb. The other thing is that even that small thickness of the UHPC that you use, it allows you, because it is so strong, it's 5 times, 6 times more stronger than a regular concrete. It allows the member size to get smaller. Member get smaller. I can put lightweight concrete inside. Now the total weight of the structure gets smaller. The foundation size gets smaller. UHPC now is allowing us to make our structure resilient against extreme event. It allows us to develop structures that are almost maintenance free. And also it makes the very fast construction. It's a form of ABC. The contractor cannot say, I don't have experience. What do you mean experience? I mean, you've got the element, you just stack it on top of each other. There's nothing. Because the contractors usually like to beef up the prices because of perceived risk. So this is a fantastic, great idea. I think it's a future. Now, some people, I will say this one, and some people have accused me of being more of a steel guy. I look at what is the best way to build the structures. I don't care if it's a steel. I don't care if it's a concrete. But I can tell you that over the last 4 years, 95% of my research has been on the UHPC, because I truly believe that that's the future of the structural engineering.
Okay, let's pull back a little bit and talk about UHPC. Some of our listeners may not even be familiar with that term. So can you just give us a general description of what ultra high performance concrete is and what makes it so revolutionary and effective?
Yeah, ultra high performance concrete, the mix is similar in a sense to regular concrete, but we don't have a coarse aggregate. It's a very fine aggregate. It has a very low water cement ratio, very similar to high strength concrete that was back in the late 80s, early 90s. The major difference is that in the UHPC, we use lots of steel fibers. And that's what actually adds to the cost. The reason for the cost of the UHPC to be high is because of the fact that we are using a steel fiber. So you are using more cement, usually cement type 1. Use a water cement ratio of something in order of the 0.2, 0.22. You don't want to go higher than that. Use basically a sand as an aggregate. It's a very compact material. That's why nothing goes through it. And then you use lots of high range water reducers because you have a very low water cement ratio. So to make it flowable, to make it workable, that's why we use a high range water reducers. And then we use lots of steel fiber, like 250 pounds of steel in 1 cubic yard. So that's it. That's quite a bit. So it's a 2%. We usually use a 2% by volume of the material is the steel fibers, and that's a very small steel fibers, very high strength, about 300-400 ksi steel fibers, very short and very small diameter. And then the material, the UHPC, first of all, the strength is about, could be anywhere between 18 and 30 ksi. So, and then, but the post cracking, once the cracking forms, you can sustain that basically the tensile strength. So the tensile strength could be about the 0.8 ksi, which is very good. So it has a good tensile strength too. So that's what really the UHPC is. And a good thing is that in the Europe, they've been using this UHPC for a number of years for upgrading, strengthening deficient structures.
When we look at specifications for materials, a lot of times these materials are tested based on conventional properties such as strength. And as you mentioned, just in the example you gave for strength, that strength is going to exceed most designs for typical concrete strength anyway. So like you said, it's kind of it's just there. It's assumed it's going to be strong enough. So are there some tests that we should be thinking about to determine the quality of the ultra high performance concrete rather than strength?
There are standard tests that you can use, like rapid chloride permeability numbers, for example, to assess the durability of the material, freeze-off cycle. For example, there are a standard ASTM test. With respect to the UHPC, there's one additional test that the Federal Highway Administration have suggested. The Ben Grable and his group has done a wonderful job at FHWA, and that's a direct tensile test, basically. And so there is a specification for that. Another thing with respect to the UHPC that has been kind of lacking is a specification, because structural engineers like to have an ACI code or AASHTO code. So that is working. So the AASHTO is working. I think the draft is out. The draft of the design provisions for the UHPC. AASHTO has led. There's no standard. There's no ASTM because that takes I think a long time. I believe probably that was one of the motives to go through the AASHTO. So the AASHTO design guide for the UHPC should be out fairly soon. In fact, if anybody is interested in that, if they go to our website, ABC UTC website, FIU, September 13th, we had a 4-hour webinar that's going to be archived soon. And Ben Grable actually gave a presentation on the upcoming specifications for the design of the UHPC. And if they're interested in how do you produce non-proprietary UHPC, they can go to the same in-depth webinar that we had at our ABCUTC website. So that gives you all the information that really you need, how to produce it, how to test it, and everything that you need to know from A to Z about the UHPC.
Great. And we will have a link to that for our listeners on our website, along with this podcast episode. We'll put some links that are relevant for you so that you can learn more about it. Now, we talked about design. We talked about the 3D printing process. Are there any other processes that can be used for fortifying existing structures that may be experiencing inundation with seawater or something that could lead to rapid corrosion?
I think that one of the best use of the UHPC is retrofit and upgrade and be proactive, especially in case of the coastal areas. I mean, if you have a bridge that is being exposed to salt water and so on, the best way is just to put a layer of UHPC around it. So we have developed the technology right now actually to retrofit and upgrade concrete columns, timber piles, using UHPC. The use of the UHPC for a bridge overlay is taking off right now, because you can take a top layer of the bridge deck and then and expose some steel reinforcement, or you can add some steel reinforcement and then just cover it with the UHPC rather than a silica fume overlay or whatever you have. And that will not only add to the strength, but it will add to the resiliency and prevention of the corrosion. So we have a tremendous amount of activities in that area right now, and trying to beef up, upgrade, retrofit existing structures using a UHPC.
One technique that I heard about recently at a meeting was using it in Shotcrete application. That kind of surprised me, especially with the steel fibers.
Yeah.
I would have expected there to be a lot of challenges related to just being able to have that pass through a Shotcrete applicator and be able to be applied in a consistent way so that it remains in a homogeneous state as it flows through. Do you have any insight into how that application works and its effectiveness?
Yeah, you read my mind. The Shotcrete, actually, I think that's one of the best way trying to retrofit and upgrade, let's say, existing, let's say, columns you have, is a pneumatic, basically Shotcrete. We usually use a pneumatic, not Shotcrete, because the Shotcrete is a copyrighted term or whatever it is. When we started using a Shotcrete, using a UHPC, we had lots of challenges. And like you said, one of the challenges was that we were using it, basically, we had a pump that we would pour the UHPC, and then you would pump basically the UHPC that has the fibers. And this had exactly the same mix that we use for cast in place. But then the fibers would get clogged in, and then we had lots of problems with it. And we finally, after a year, we figured out what to do. Basically, we use some admixtures, VMA, viscosity modified agent, basically trying to change the viscosity of the material without changing its properties, short-term and long-term properties. Okay. And then the other thing that we learned was that we had to prime the line. So we would put basically a grout, prime the line, and then once let's say, a regular grout would come out of the nozzle, then right behind it, there was basically UHPC. And now we are able to shotcrete basically vertical surface or upside down or whatever you have. And I think we have taken a first step. I can see in future we should be able to use a shotcrete for the bridge deck overlay. Now imagine that. We are a long way from there, but I think it's doable. Imagine you go in like a hose, you just spray the UHPC on top of it. It takes you 10 hours. It's already set. You've got a new bridge, fractional cost of a replacement. I see in the future, we're moving that, but we are not there yet.
That would be a really interesting process. I imagine that would probably get the bridge to be put back into service pretty quickly too, with a process like that.
So I have a question. So if you are putting the ultra high performance concrete over the bridge, because I'm not technical, so I'm just trying to envision this. So that would basically your exoskeleton around the bridge supports, and then so anything inside of that is preserved at the same strength, and then it's adding strength on top of it. Is that what's happening in that scenario?
Actually, you're asking a good question. Okay. Let's say, for example, you have a column, right? Bridge column, and you are seeing some sort of a corrosion activity going on. Well, what you have to do, you have to, with a sandblast or water pressure, you need to remove some of the concrete. The European experience is that you don't need to remove all the contaminated concrete. You need to remove about 1 inch beyond the main steel reinforcement that there is, and then cast the UHPC around it. You have to be careful with the surface condition, because the existing column is going to have a regular concrete aggregate. You have to have a good aggregate exposure, and you have to make sure that before you cast the UHPC against it, you have to make sure that it's dampened, so there's a moisture in that interface, that surface, because UHPC doesn't have that much water in it. Water cement ratio is 0.2, and if the surface that you are casting the UHPC against is not moist, it's going to suck all that little water there is and they cause a cracking. So to answer your question, with the sandblast or other techniques, we can remove some of the concrete, and depends on how much corrosion you have, activities. You can add some steel reinforcement in there if you want to, and then prepare the surface conditions, expose the aggregate, moist basically the surface, and then cast the UHPC against this. Now, when you do that, you don't need too much material. In the case of the timber piles, it's a different. In the case of the timber piles, we concluded that you cannot rely on an existing timber pile to carry any portion of the load. So we said we're going to encase that timber pile with the UHPC and design it so that all the load is carried by the UHPC, not the timber pile. There was one major problem. Timber, depending on the moisture, can expand and contract. And so in the initial work that we did was these timber piles would kind of expand a little bit and then cause a tensile stress in the shell, the UHPC shell that you were casting against the timber pile, and cause a cracking. We solved that problem by putting a very thin layer of a foam on the surface of the timber pile and then cast the UHPC against that. And that solved the problem. You do need some reinforcement and all that. So there is some preparation work that comes in. You don't just go and just spray or cast the UHPC against the existing. You have to prepare the surface.
I'm really glad you addressed that, because that was one of the things I was wondering about, is those differences in thermal expansion, because what you're doing is you're applying something that where you've tested and thought about that on something where they did not think about that. So you could have some variability there, but yeah, that answers my question there. But I've got another tough one for you. You know, bridges aren't just a means of getting across a river or over or some body of water or a gully or something like that. They often have cultural significance. Some of them have been designed with artistry, and they have social value beyond transportation, right? So when you've got an old bridge, and this probably happens in Europe and other parts of the world that are older than America, where you've got these problems going on, can this material be used and still preserve the other value of those structures?
Yeah. I mean, you're referring to historic bridge. So the historic bridge, the appearance should not change. So UHPC is not going to solve all the problems. So I have strengthened, for example, that the historic bridge, for example, when I was at my previous institution. So any element that you put in the historic bridge that is meant to increase the capacity have to be hidden, basically. So you don't change the appearance of it. But the foundation part of it, yes. So UHPC probably is not a good application there because it may change the appearance of the bridge, and you don't want to do that in the case of the historic bridges. But the foundation part of it, yes, you could do that.
Now, one last thing I wanted to ask about is, the traveling public can misunderstand things or be concerned about things they don't need to be concerned about sometimes. And one thing that I could see coming up here is we're talking about putting little threads of steel throughout concrete, which could be used on an overlay. And I could imagine somebody saying, well, what about my tires? I'm worried about tire damage. Can you say anything to address any potential concerns people might have about that issue?
Yeah, sure. I mean, first of all, these fibers are very, very small. Okay. And there are solutions. In the cases, there has been several bridges, especially actually long span bridges, that they have put a UHPC overlays, and the contractors actually have gone back and by grinding and making this, getting rid of steel reinforcement. So that is not an issue at all, because these steel fibers is a very tiny steel fiber that some of it is stick out, but the contractors have found their ways trying to get rid of that and make it smooth. So even if somebody walk barefooted in there, so they don't get basically injured.
Sorry, I said that was my last question, but one other question I have for you, and this will really be the last one. Other than what we've been talking about today, are there any other applications or materials that you're particularly excited about in the future beyond what we've been discussing right now?
Yeah, I think if I look at the crystal ball, that what holds in the future, I see several things. Automation, I think, is going to play a major role in the coming years. It's not a science fiction anymore. I mean, different industry have moved into the automations, and the construction industry has been fairly slow. But believe it or not, actually, bridge industry is ahead of the building industry when it comes to the automation, like 3D printings and things like that. The other thing that I see with respect to the bridge structures, that I see major changes that are being incorporated. I think technologies, advanced technologies are finding their way into bridge engineering, like artificial intelligence, for example. So the decisions that we were making based on just one's experience, now you can couple that with artificial intelligence in order to make a better decisions. The other changes that I see, that, for example, that we are paying more attention now in making all the decisions that we are making, is now we are considering, it's going to be more and more the safety, the mobility, the resiliency, the social equity, for example. These are the factors that really goes engineering. Bridge engineering is just like you said. I mean, it's not just building a really bridge. I mean, you shut down, for example, one bridge. I mean, that can have a really significant impact on the businesses. I'll give you one example. Actually, I come to the TRB, of course, every year. I believe it was in 2019. There is a restaurant that I really like in the Washington, D.C. area. I went 2018 and I went 2019. They were replacing one bridge, and it was in a street that there were lots of restaurants. And there's one restaurant I love. So anytime I come to Washington, D.C., I go there just because of the food. And every time I went, there was a big sign too that I don't know what agency is building a bridge over here. And these poor businesses on the side, they were suffering basically from that because the construction was going on. And I talked to actually one of the business. I said, do you guys know that you can probably replace this bridge over a weekend? He said, oh yeah. I said, yes, there's something called accelerated bridge construction that you can. So these are not the decisions that we are making. I think it's going to change the way. There's going to be more tools available for the decision makers, okay, not just the structural engineers, to make decision that accounts for the resiliency, climate change, social equity, impact on the businesses, and so on. So, you look at the 1940s, I think during the time period that we built the Golden Gate and the Manhattan Bridge and all that, you look at it, the amount of the different innovative technology that was incorporated was tremendous. But then you see a gap a little bit, things are steady, right? But now I can see that with this artificial intelligence, monitoring, sensing, and blockchain, advanced materials, automation, 3D printing, I see exponentially we are going to, our bridge industry is going to really move forward is much faster way because of all these advanced technologies. And the credit to the USDOT, the USDOT is putting lots of emphasis now on advanced technologies such as the automations, 3D printing, and so on. The bridge engineering is going to move. I can see in the next 10 years, it's going to look nothing like what we have right now.
Yeah, that's exciting. And I think that, like you mentioned, a good example of what is in it for us, not just as the traveling public, but just the public in general, people who have restaurants, people who just want to have a better life. So, Atora, I really appreciate your time today. You've covered so much of this in such a great way, and you've given us a lot to think about. I'm excited to see what comes next. And if somebody has any questions or follow up, where can they get in touch with you or get more information about what you've been working on?
My email address is very simple. Just contact me through the email address aazizina@fiu.edu. So just send me an email. I will be more than happy to talk with anyone that wants more information on what we do. So we'll be happy to do that.
All right, sounds great. Thank you very much.
You bet. Thanks for the opportunity.
Thanks for listening to AASHTO Resource Q&A. If you'd like to be a guest or just submit a question, send us an email at podcast@ashtoresource.org or call Brian at 240-436-4820. For other news and related content, check out AASHTO Resources Twitter feed or go to ashtoresource.org.